Oh, I tell you, Will, this old vise sure is heavy.
Oh, that's because it has to be so strong. We're going to be clamping down some big pieces of material, hammering. That's made out of solid iron. That's got a lot of weight.
That's right. You know, that's one of the biggest problems that faces anyone who tries to construct an aircraft. That's weight. As we made larger and larger aircraft over the years and stronger materials, the weight just kept increasing. Finally, in 1903, when we added an engine, it shot up to over 600 pounds.
Yeah, weight's the enemy of all aircraft, and it never sleeps. Actually, weight's just an expression of the gravitational force between two masses. Because the Earth is so massive, all objects on the Earth are attracted to the center of the Earth. This idea was actually worked out by Sir Isaac Newton back in the 1600s. And he expressed it with this equation. The force between any two objects is equal to a gravitational constant, g, times the mass of the first object, m1, times the mass of the second object, m2, divided by the square of the distance between them. Now, what this equation tells us is that if m1, the mass of our aircraft, increases, well, then the force that's being pulled down to the center of the Earth increases. The weight increases, and we're going to have to overcome that.
That's right. The challenge then as an aircraft designer is to minimize weight and yet maintain enough strength in the structure so the aircraft can withstand all the forces of flight. Our solution to this was based on a bridge design called a Pratt truss. We had two lightweight, hollow, cloth-covered wings held apart by thin wood struts, and the whole structure was braced by thin yet strong metal wire, just like a Pratt bridge. Our plane was mostly, as you can see, empty space.
Do you remember back to Kitty Hawk in 1901? We had a friend who asked us to do some testing of his aircraft, and he was going to try to save even more weight by replacing the wooden struts with cardboard tubes. Well, unfortunately, when the weight of the pilot was added to this craft, it simply collapsed because the structure lacked the strength to support the total weight. The game for an airplane designer is always one of balancing weight of the aircraft and strength of the aircraft.
We had the same problem in 1903 with our first powered aircraft, which we intended to fly, remember, at the end of September.
Yeah.
In order to save weight, we decided to use hollow tubes for propeller shafts. When tested, they bent because they could not withstand the stress of the engine and the chain drive. When the first set bent, we sent back to Dayton for a second set. When those also bent, we determined that we had to accept the weight penalty. So I went back to Dayton and had solid steel propeller shafts machined. All that delay is the reason the first flight didn't happen until a very cold day in December.
The important thing to note here is that we measured the amount of power that our engine was going to provide, so we had a good estimate of how much lift the aircraft could generate. Our problem then was to control weight, and we did that by calculating the weight of every one of the components of our aircraft: the elevators, the rudder, the wings, all the struts, the motor, the fuel, the pilot.
Funny you should mention the pilot. You know, in those days, my brother and I weighed less than 140 pounds, and we could be picked up by our aircraft. If we were 200-pounders, we never would have flown.
That's true. In fact, when we were trying to sell airplanes to the Army in 1908, that required that we carried a passenger along besides the pilot. So our choice for that passenger was Lieutenant Benjamin Foulois, because he only weighed 120 pounds. Weight is everything.
That's right. He was perfect. Think of it, though. You must pay a price for every ounce you try and lift off the ground. The next time you enter a modern aircraft, look at all the lightweight materials and the hollow construction they're used just to save weight.
You know, you've got me thinking about the weight of this vise. Now, that vise is made out of solid iron. What do you suppose it weighs? Just,
I guess about 30 pounds.
okay, about 30 pounds. Now, suppose instead of making it out of solid iron, we made the same machine, same size, but made it out of a lighter material like aluminum.
Okay. Okay. Oh, I think I know where you're going.
Okay. Do we have some information about that?
I do.
Okay. Let's just for fun.
Okay. 1 cubic foot of iron
Okay.
would weigh 450 pounds.
All right. 450 for iron.
1 cubic foot of aluminum would weigh 165 pounds.
165 pounds. So that's about a third. So then for the same size vise would weigh,
About 10 pounds.
yeah, that'd be pretty easy for you to bring in here.
A lot less work.
A lot less work. You know, it's interesting because when we built our engine in 1903 and our 04 and 05 engines, we used cast aluminum blocks. At the time, most automobiles were using cast iron blocks. Now, our engines came in at about 180 pounds, right? If we would have used cast iron like on an automobile engine, what would that have come up to?
Let's see. I think I can figure it. You can figure
Okay.
it too. Oh, I got 6. I got about over 400 pounds.
Over 400 pounds. So we would have to then build our wings even bigger to carry the 400 pounds, the additional 300 pounds of the engine in, and then we'd have to carry the weight of the wings as well. So weight is always a problem. And I've got an idea, actually, for how to save a little weight.
Oh, that's a good.
Okay.
That's anything.
Yep.